An event happens where a neurotransmitter is released from cell A into the synapse of cell B. Four things can happen. One, it could dissipate or float away. Two, it could reuptake and be taken back up into cell A. Three, it could be metabolized by enzymes. Or four, the most important, it could bind to the binding site of the postsynaptic receptor. When we take a closer look, the synaptic vesicles emptying into the synapse, binding to the binding site of the postsynaptic receptor, which is the dendrite of cell B. When we take an even closer look, neurotransmitters are passing through the receptor. Outside the lipid bilayer, we have interstitial fluid, and inside we have cytoplasm. The receptor is open. Normally it's closed until the neurotransmitter binds to the receptor. The neurotransmitters are passed through the cells by two forces, osmosis and electrostatic pressure. Osmosis pushes particles down the concentration gradient, and inside is slightly negatively charged. But because opposites attract, sodium, which has a positive charge, enters the cell. When discussing the oscilloscope, it allows us to know what exactly is going on between neurons, and it measures their millivoltage, and at rest the cell lies at negative 70. The neurotransmitter approaches and opens a receptor, translating on the oscilloscope that there is a slight rise. The rise on the oscilloscope is called the EPSP, excitatory postsynaptic potential. It is created when the ionotropic receptors in cell B are open due to the presence of neurotransmitters binding to the cell. When there are multiple neurotransmitters binding to a cell, it is called a summation. In the picture, there are multiple EPSPs adding to each and adding positively to the cell. When there is a large amount, it reaches the threshold of excitation measured at negative 65 millivolts. Reaching the threshold of excitation at negative 65, all neurotransmitters are accounted for at the axon hillock. The process the neurotransmitters goes through causing the cell to reach the threshold of excitation causes the temporal or spatial summation. The summation activates voltage-gated channels due to the force implied on the cell from the neurotransmitters. Then and only then will the voltage-gated channels open. This is the view from the oscilloscope. At number 1, the cell is at rest, which is at negative 70 millivoltage. Number 2 is where the cell hits the summation. Number 3 is an illustration of a cell at the threshold of excitation at negative 65 millivoltage. At 4 is a major depolarization where sodium enters the cell, moving the millivoltage from negative 65 to positive 55, which will put sodium at its equilibrium. Number 5 is where we then see a massive hyperpolarization where potassium leaves the cell in search for its own equilibrium that is reached at a negative 75 millivoltage. As sodium and potassium pumps, then they then bring the cell back to at rest at a negative 70 millivoltage. Neurotransmitters have an all or nothing type of behavior. Action potential completes this journey through the neuron beginning at the axon hillock. It then reaches the edges of the myelin sheath and then spreads like a wave to the next node of Ranvier, and then so on and so on. Shown here are the potassium and sodium gated channels. The sodium gated channels allow particles into the cell, whereas the potassium gated channels move particles out of the cell. The action potential is generated at each node of Ranvier, located at 1, 2, and 3. The action potential moving from one node of Ranvier to the next is called saltatory conduction. Coming to the end of our neuron story, where the action potential reaches the terminal button, interacting with calcium at this point, the vesicle then binds to the inside of the presynaptic membrane and is open to a process called exocytosis. The neurotransmitters are then floating to the synapse between cell B and cell C. The end.